Welcome to the course Structure Analysis. I am Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So today we are at the 25th lecture, Moving Loads for the Severed Point Loads. So in last lecture we had discussed how to construct the shear force diagram and then bending moment diagram by using the moving load concept, and then moving load is single point load. Okay. So in 25th lectures we are going to see if several point loads are moving across the girder, how to compute the maximum positive shear force, maximum negative shear force, maximum bending moment, absolute maximum bending moment, absolute maximum shear force values. So at the end of the lecture, student can able to analyze the response of a simply supported girder under a system of multiple or several moving point loads. So several point loads or multiple point loads crossing the girder, you see here there is a system of load we can able to see, which is 6 kilonewton, all are kilonewton, okay, 6 kilonewton, 8 kilonewton, 20 kilonewton, 18 kilonewton and then 12 kilonewton spaced equal interval 2.5 meters crossing the girder of span 22.5 meters from the point A to the point B. Okay, what is the first component? First component I am going to calculate the maximum negative shear force. So from the single point load already we learned, for calculating the maximum negative shear force we need to keep the head of the load at the point C or where the X section occurs. Okay, so point C where we are taken here at the center of the beam. So in the problem also has to calculate all the values at the section C. So before that I just want to tell you what is the head and tail of the load. So this is the head of the load and then this is the tail of the load. So here what is kept? We need to keep the head of the load at the point C. So I kept the head of the load at point C. So you know the total distance is 22.5 meter span, L, total L is equal to 22.5 meters. In the half of that it's 11.25 meters. So I am keeping the head of the load is nothing but 12 kilonewton at the point C and the remaining loads are before that it is there. Okay, accordingly I will be writing the distance also 11.25 minus 2.5 minus 2.5 minus 2.5 minus 2.5, then finally I will be getting 1.25 leftover distance. So it's a system of arranging the loads. Then what I am doing? I am saying all the summation of moments at the support A is 0. We know simply supported beam means both the support moments are 0. So taking moment at A, what else I am going to have? This RB perpendicular distance is a full span which is 22.5 and then this load minus 12 is acting at the distance of 11.25 and then minus 18. Remaining distance you can see 2.5, 2.55, 5 plus 2.5, 7.5, 7.5 plus 1.5, 8.75 and then this minus 20 multiplied by 6.25, you see 2.5 plus 2.55 and then this 1.25. So, we will be getting 6.25 and then this minus 8 multiplied by 3.75, it is just a linear distance from that load to the left support, that is support A. Then minus 6 multiplied by 1.25, that is it, you see. So, we have the reaction forces multiplied by the perpendicular distance and then we have the load is acting downward direction, that is multiplied by the perpendicular distance, equated to 0 because the moment at support A is 0. Now what is the maximum negative shear force? You see, in between RB to the section C no other loads are there. That means what? RB alone is the shear force. So since I am calculating the maximum negative shear force is nothing but minus of RB. So minus of RB is nothing but minus 20.22 kilonewton. This is the maximum negative shear force. If you want the maximum positive shear force, we need to keep the tail of the load in the XX section. For negative shear force, we need to keep the head of the load in XX section. For positive shear force, we need to keep the tail of the load in the XX section. Here I am calculating the RA value and taking moment at B is equal to 0. So we know that the tail of the load is 6 kilonewton which is kept at the point C. So I am going to calculate the RA value. So load multiplied by perpendicular distance. So minus 6 into the remaining distance is 11.25, minus 8 into the remaining distance 8.75, and then minus 20 into the remaining distance is 6.25, minus 18 into the remaining distance is minus 12, and then minus 12 into the remaining distance is 1.25. So finally I will be getting the RA value. You see, from the RA to the distance from here to here, no load is there except what? The RA itself. So RA itself is the maximum positive shear force value. Now calculate the absolute shear force value. Already I told you absolute shear force going to occur any one of the support. What it means? I am going to keep the 6 kilonewton load in the support A. Then calculate the value of RA. Then I am going to keep this 12 kilonewton load at the support B. Then I am going to calculate the value of RB. Okay, what exactly it means? Keeping the tail of the load at the RA, calculating the reaction force. Keeping the head of the load at RB and then calculating the reaction force. So you see, when I am keeping the RA at the left support, I am calculating RA. So RA multiplied by the remaining distance, so and so loads also, then we'll be getting RA is 47.33. So okay, similarly, now what I am going to do the second case, I am going to keep this 12 kilonewton at the support B. If you keep so, and then we are calculating the RB value, I am getting 52.2 kilonewton. So among these, which value is greater? Whether the RA is greater or RB is a greater value? Definitely RB is a greater value because it's a 52.2 kilonewton. So the absolute maximum bending moment is the maximum of these two values is called as the absolute maximum shear force value. Okay. So and then what else we need to calculate? We need to calculate the maximum bending moment and also the absolute maximum bending moment. So here I am calculating the maximum bending moment. Before that you can see the shear force construction. So this 15.35 is the maximum shear force value, and then minus 20.22 is the maximum negative shear force value, and this is the shear force value at RA when we are keeping the tail of the load at A, and this is the maximum absolute shear force value which is 52.2 kilonewton when we are keeping the head of the load at the RB. So through this we can able to construct the shear force diagram. Now you see, finding the CG of the load for a maximum bending moment, we have a system of point loads. We need to calculate the CG of the load. How to calculate? It's very simple. First we need to draw the system of load diagram here with by mentioning the load intensity and also the distance. Now I am just considering, I am taking point moment at this point A and starting from also this point alone. So this 6 kilonewton doesn't have any perpendicular distance. That's why 6 multiplied by 0. And then this 8 kilonewton multiplied by the linear distance is 2.5 meters. That's why 8 into 2.5 we can able to see here. And then the 20 kilonewton multiplied by 2.5 plus 2.5, 5 meters. Okay. And then 18 kilonewton multiplied by 2.5, 2.5, 2.5, totally 7.5 distance. And then this 12 kilonewton multiplied by from here to here the distance is 10 meters. In denominator I am going to put the summation of all the loads so that I get the centroid, all the forces resultant where it is acting I have calculated. We can also call this in other terms, it's called as a CG of the load. For example, this pen is there, at some point I can able to balance this pen. That point is nothing but the CG of the pen. So I can keep on adjusting, you can able to see at some location the entire pen weight is effectively transferred. If at all I move right hand side direction, then this pen will fall. Similarly, several point loads are acting. Among that load, where the CG of the load is acting. So that's what we are calculating. The CG of the load is acting at the distance of 5.86 meters. So what I am doing, what is the distance between the resultant force? So the series of loads are there. This is 12, this is 18, and this is 20, and this is 8, and then 6. Okay. From this is a 0, from here to here it is acting exactly at 5.86 meters. So the distance between the 20 kilonewton and then the resultant force is 0.86 meters. Okay. So what I am doing, that 0.86 meters by 2, which is nothing but 0.43 meters. So this is my XX section. I am exactly keeping my XX section 0.86 meter divided by 2. So accordingly I kept it. You can able to see from here to here the distance is 0.43, and from here to here distance also 0.43. In middle of that I have my XX section. So right hand side we have the resultant force and left hand side we have the 20 kilonewton load. Now what I am doing, I am just considering summation of all the moment acting at the support A is 0, and then I am going to calculate the value of RB. So RB multiplied by the perpendicular distance is 22.5, and then minus 12 into remaining distance, minus 8 into remaining distance. So far I have calculated the value of RB. Then next what I have to do, here I will clearly explain. Okay, so this is our system of loading. Let's mark all the load. This is 12, this is 18, and this is 20, and this load is 6. In between the distance are 2.5 meters, 2.5 meters. Where our resultant is acting exactly at the, it seems I have missed one load, yes. So 8 kilonewton this one, and then further we have, this is 6 kilonewton. Okay, so this is the 8 kilonewton load. Now you see this is also 2.5 meters. From here to here the CG is acting exactly at this location, which is 5. You can able to see here 5.86 meters. Now I am just going to draw the free body diagram of this alone. So this is 20 kilonewton and this is 18 kilonewton. In between our CG, this distance is 0.86 meters. So just cut it here. I am going to keep my XX section here. That's what I did it earlier. So here what I am going to do, from here to here the distance is, you can able to see, the remaining distance is 1.64 meters. So this is 1.64 meters divided by 1.64. I am going to do it here, which is 0.82 meters. So now I am keeping the XX section at exactly at 0.82 meters from the resultant. Once again calculating the value of RB, I am getting the RB value is 29.66. Now taking the moment under the 18 kilonewton load. So earlier what we have done, we have calculated the moment under the 20 kilonewton load. We have calculated the moment under the 20 kilonewton load, which is 283 kilonewton meter. Now what we are doing, we are going to calculate the moment under the 18 kilonewton load and then calculating the bending moment value, which is 279.35 kilonewton meter. Among these, which value is maximum? The maximum value is 283 kilonewton meter. So that is my absolute maximum bending moment. Okay, so in similar way, what is the 2 point loads are crossing the girder? The similar procedure only. First head of the load I need to keep in the XX section. So calculating the value of RB and then the maximum negative shear force. The second case I am going to keep the tail of the load in the XX section and then calculating the RB value and then the maximum positive shear force. Okay, absolute maximum shear force is nothing but you keep the tail of the load at A and then calculate the RA value. You keep the head of the load at B and calculate the RB value. So this is another example, but instead of several point loads, we have only 2 point loads. And then we constructed the diagram also. This is the maximum negative shear force and then this is the maximum positive shear force and then this is the absolute shear force at support A and then absolute shear force at the support B. And then the maximum bending moment. So here why I have included another example also. when several point loads are involved, it's very difficult to understand because clumsy of text. But you see here only 2 point loads are there, and then for that I have calculated the centroidal distance. The 75 kilonewton multiplied by the linear distance is 0, and then 50 kilonewton multiplied by the linear distance is from here to here it is 4 meters. So 4 multiplied by 75 divided by 75 plus 50 will give you 1.6 meters. What does means? So total distance is 4 meters. Here I have 75. Here I have 50. The CG is exactly acting. So this is a 2 meters now. The CG is exactly acting. Let's take a different color for a better understanding, green color, at this distance, which is 1.6 meters. Now what I have to do, you know, this 1.6 I will divide into 2. Okay, 1.6 divided by 2 is 0.8. There I will give my XX section. I keep the load accordingly and then calculate the value of RB. Okay, so the maximum bending moment under the 75 kilonewton I have calculated. After calculating RB and RA, what I am going to do? I am going to take the moment under the 75 kilonewton, which is nothing but just RA into 5.2. I got the value of maximum bending moment under the 75 kilonewton load. Similarly, I need to calculate the maximum bending moment under 50 kilonewton load also. So, from the resultant to the 50 kilonewton load is 1.6 meters. So, what I have to do? I have to put, so 1.6 meters, how much it is? So, this is 1.6 meters, okay. From the resultant to the remaining distance, that is 2.4 meters divided by 2. Clearly, I will write here. We have calculated for this load, this is 75 and this is 50. So, our CG is acting 1.6 meter distance. Total distance 4 meters. What is the remaining distance here? 2.4 meters. So, already I have divided this and then calculated. Now, I need to divide this 2.4 meters and then calculate the bending moment under the load 50 kilonewton. Okay. So, under the 50 kilonewton I have calculated the RB value is 50 and then taking the moment under the 50 kilonewton. So, this RB multiplied by where the 50 is located at 4.8 meter distance. That is why 50 multiplied by 4.8 meter distance I am getting 240 kilonewton. Now, you see whether the 240 is maximum or 281 is maximum. Obviously, 281 is the maximum. So, that is means 281 is the absolute maximum bending moment. So, this is the value is the absolute maximum bending moment is 281.68 kilonewton meter. Okay. So, we can able to see the bending moment diagram also. This is the absolute value and this is the bending moment value under the 75, this bending moment value under the 50 and then bending moment value under the 75 kilonewton. We have the bending moment diagram. So, from this lecture, what we have learned? We learned how to calculate the positive shear force value, how to calculate the negative shear force value and also maximum bending moment, absolute maximum shear force and also absolute maximum bending moment, how to calculate for a multiple point loads or several point loads we learned from this lecture. Okay. Thank you for watching this lecture. Thank you.